let this circle represent the Earth, and we want to find the moment of inertia of the Earth. Now, the density of the Earth is a function of our distance from the center. So I'm going to let rho stand for distance from the center. So rho is the distance from the center, and rho is going to go from 0 to big R, where R is the radius of the Earth. Now, if you know a little bit about the structure of the Earth, and if you know a little bit, you probably know more than I do, but the basic idea is the Earth is composed of layers. The inner layer is very dense. It's basically compressed iron. Has a density of around 13 grams per cubic centimeter. So I'm just going to express the density in terms of, let's say maybe about 12. Okay. Density decreases as we move out, and it doesn't decrease linearly, it decreases by layers. It gets a little less dense in a given layer, but then the material of which the layer is composed changes, so the density goes down substantially with every new layer. And there are several layers. I'm not going to make an accurate graph, but the density kind of goes down. Then we go to another layer and it goes down a little bit. Then we go to another layer, it drops off, and we go into another layer. It drops off during each layer, but it drops off most significantly when we move from one layer to another. Once more, decreasing about from 12 to 3. Now that would be actually in grams per cubic centimeter. I think I might have mentioned that, but we're not going to do this in those terms. So I'm just going to let the density be absolute numbers here. And I'm going to say that if we just sketch a straight line from here to here, we have a straight line approximation. Now, what's the line? The line has a vertical intercept that we'll say is about 12. So we will say that the density is approximately equal to 12. And then we're going to add the slope times the value of rho. What's the slope of this line? Well, it decreases by 9 over a distance of r, so that's going to be 12 minus 9 over r times rho. Now, with respect to the density function, I'll just comment that this is what you get if rho is the distance from the center. Of course, rho equals square root of x squared plus y squared plus z squared. In rectangular coordinates, it equals r squared plus square root of r squared plus z squared in cylindrical coordinates. So we could say that, first of all, in terms of rho, the density is 12 minus 9 over r times rho. Make sure we're on the page here. Okay. And then delta could also be expressed, the density, in terms of x, y, z. And that's simply going to be 12 minus 9 over r times rho. And rho is the square root of x squared plus y squared plus z squared. It's written a little bit small, but should be legible on full screen. Alternatively, in terms of cylindrical coordinates, r, theta, and z, you'd have 12 minus 9 over big R times the square root of little r squared plus z squared. We can set up the moment of inertia integral in any of these coordinate systems, and that's actually what we're going to do. We're going to calculate the moment of inertia in spherical coordinates using rho, and rectangular coordinates using x, y, z, and in cylindrical coordinates using r, theta, and z. Now, in spherical coordinates, we can depict the situation. We could have a typical increment at distance r, or distance rho, from the origin, with coordinate theta and coordinate phi, and if this is a specific point, let this be the sample point, so we're going to call this rho sub I star, theta sub j star, and phi sub k star. So what we have is a sample point, rho I star, theta j star, phi k star. And that's within an interval. I'm going to call that an increment, and I'm going to fix that. Okay, I'm going to say within a volume increment defined by delta rho, delta theta, and delta phi. The density is simply our density function, 12 minus 9 over big R times rho. Let's make that times rho sub I star, because we're talking about the density within this sample interval. Question is, what's our volume? What's the volume of the increment? What's delta V I j k? What is that? It's not just delta rho times delta theta times delta phi. Delta theta and delta phi are in angular units, radians, and delta rho's in units of distance. When we multiply distance by angle, we don't get units of volume, so we know that that can't be right. It's not delta rho, delta theta, delta phi. And of course we know from consideration of polar coordinates that if we have polar coordinates r and theta, that the size of the increment corresponding to angular deviation of delta theta is going to depend on how far we are from the origin. And it should be clear that we're going to have a similar situation here, that the further we are from the origin, the bigger change in phi is going to, the bigger effect a change in phi is going to have on our volume, and the bigger the effect of a change in theta. So we're going to digress for a minute and ask ourselves just what to do about this volume increment. So we ask the question, volume increment in spherical coordinate system. We'll look at that in the next clip, and then we'll come back and figure out the moment of inertia of the Earth.